Welcome back to ECE 441A, 541A. We're having breakfast, apparently, trying to get our energy level up. This is the last day of class, and your final exam is less than a week away. It's on Tuesday, and it's at 10:30, so that gives you a little bit more time to eat breakfast. Hopefully it gives you more time to sleep. You know the importance of sleep, I hope, at this point in your career. There's a lot of things that are due today, and one that students are wanting to know is, when do I have extra credit, or is there extra credit? Maybe I'll give you extra credit if you fill out the TCE. And the way that I will have you do that, maybe we'll say if 80% of the class completes the TCE, then I'll give everyone extra credit. But it has to be the particular section. There's 3 different sections of this class. There's a section 1 in 441A, there's a section 1 in 541A, and there's a section 201. So depending on your section, you want to rah-rah those students to try to get 80% of that. Pardon? The current percentages is the 441A class is much lower. It's about 30%. So you need to raise it up a level to get it to 80%. I think the highest percent might be the, oh no, I have too many. I have 5 different sections I'm trying to keep track of, so who knows which ones are where, but I think 441A is the lowest, and I feel a little disappointed maybe in that fraction. There are some office hours. The normal ones are Wednesday, Thursday, and Friday, and then there's some new ones on Monday. We don't normally have office hours on Monday, but we don't normally have an exam on Tuesday, meaning next Monday from 12:30 to 2:30 will be office hours. And what I want to do today is listed here. 1, we'll talk about the final exam process. And the topics for the final, I gave you those on the first day of class. I gave you the final exam. If you raised your hand and said, will it be on the exam, I can just point to the syllabus and say, you've had it all semester. So we'll look at page, I'm not sure it's page 4, it's page 5. I extracted it. It's one of the pages in the syllabus. So I don't think it's page 4. I think that's a typo. Somebody didn't type right when they were writing this up. So I think it's page 5. We'll look at when you might use a phase lead or a phase lag controller, or I'll just direct you to a table that you can now see this column of reasons behind using one controller versus another. We'll show some analog realizations. If you like to think about circuits, some of you don't get apprehensive if you don't like circuits, but just op-amp realizations of different controllers, a PD controller, a PI controller. Now you can physically see what that transfer function looks like as a circuit realization. And again, those are tables or pictures in the book that we will simply scroll through. Then we'll return or recap our comparison on the controllers, the output feedback control and the full state feedback control. And if we have time, we will actually show how we can enjoy the benefits of integral control when we have full state feedback. Or if we don't get to that, that's called the internal model approach in Chapter 11, which is one of the later sections. It won't be on the final, so you can lay your head down after your full breakfast when we get to integral control, if we get that far, and just take a nap if you don't want to listen to it. But it's very interesting material. Of course, that's relative, I guess, to who's defining interesting. Final exam process. It's comprehensive, 15 questions. It's not multiple choice. 4 sheets of notes. I think you've had 3 up to this point, and it's trying to now be uniformly distributed over the entire course, meaning the material that we've covered, homeworks 8, 9, and 10, will be addressed on the final exam. Even though we haven't had a midterm exam cover that material, You will want to be, if you choose not to do those homeworks, you need to know how to work those before the final exam, because that can be one of these 15 questions. And it could be 3 or 4 of the 15. So you don't want to completely dismiss what you haven't done or what we've done since exam number 3. You can bring in, you provide table 2.3, which is Laplace tables. Then what instruments can you bring? Something to write with, a calculator, a straight edge, a protractor. That's probably all you'll need. You probably don't need to bring a compass or dividers. But if that makes you feel good, you can bring those in. I won't take those away from you. But I will take away your computer, your cell phone, your textbook, course notes, and I'll take your neighbor away if you start conspiring on the exam. Any questions on the process of the final? That should be very consistent with what we've talked about or done all semester. See here, page 5. Final exam topics. I want to just do this, but you guys have young eyes. You can see that. But you can see there's a list of 17. So if you have a 17-sided coin, you could roll that coin. 15 will come up. 15 of these 17. So if you want to lay odds on which one's not going to be on the final, you can try that, but I would try to focus on all 17. And if you can do these problems, forwards, backwards, in the middle, etc., you should be fine on the final exam. But that's a copy of the material, and you can see how after exam number 3 plays into at least 3 of those topics. You better be able to do gain margin and phase margin by a given Bode plot. Now on homework 9, if you're struggling to try to meet those design objectives, on the final you just have to sort of go through the process once. You don't have to check your work. You can now try to find the crossover frequency or the omega sub m, and then get an alpha, and then find the 10 minus log, and you're just eyeballing these locations on the Bode plot. That's fine, as long as it seems reasonable. If it's between 1 and 10 on the frequency axis, and you say, oh, omega sub m, I want it to be 32, I'm going to say, no, 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 that's not quite between 1 and 10. So you should be able to eyeball it pretty well, knowing the relationship between log of numbers and this log of omega axis that you're dealing with or playing with on a Bode plot. But again, if you can work these topics, forwards, backwards, in the middle, you should be okay on the final. Controller types. Here is a table, table 10.6 in the question. So there's one page on, the question is, I see there's one practice final. Let me modify that question. There's no practice final. There's just one page under final exam material, and that one page covers some material that I had on a previous exam number 3 that dealt with Bode plot stuff. So it's just like identifying a system, the inverse Bode problem, which is, given the frequency response, can you determine a G of S? And there might be a phase lead or a phase lag design. I don't remember. But that's something that was on a previous exam that I had available. I'm not giving you a practice final exam. So don't keep looking, going back to the course website and saying, oh, he hasn't posted, he hasn't posted. It won't be posted. So just work from the previous exams, homeworks 8, 9, and 10, and that list of topics. In terms of phase lead and phase lag, which controller doesn't slow down the system response? Phase lead. If you're okay to slow the system down, then you can tempt a phase lag controller, and you're now making the phase crossover frequency occur at a lower frequency value. But this tells you in words what the approach is trying to do, what you can expect in terms of results, some of the pros and cons, and when you might or might not want to apply a phase lead versus a phase lag controller. But you will want to be comfortable with, if I say, don't slow the system down, then which controller am I asking you to design? Don't slow the system down, phase lead. If I say you can slow the system down, then phase lag is okay. If I don't say, then you're on your own. And depending on what the question is asking, that may allow you to design phase lead or phase lag, either one. It may just depend on what's being asked. If you were curious how you might realize in a circuit a PD controller, proportional derivative, or a PI controller, or a lead lag controller with circuits, this is how you could create those. Meaning, as a review for the final, you could try to find the transfer function between, in the lower picture, V sub I and V sub naught. And you should be able to derive that transfer function. And now you can see how you can adjust the time constant of the zero factor, the time constant of the pole factor by the choice of R1C1 and R2C2, respectively. And then you can adjust the overall gain by the collection of these resistor values, R4, R2, R3, and R1. Or if you wanted to do a PI. If you wanted to go all in and do a PID, here's a PID controller. And that might actually be a homework assignment or a problem in AP 2.9. I don't think that's the right figure. It's more like, oh, yeah, that's the right figure. It's just in a funny chapter. It's in chapter probably 10 of the textbook. But this will now give you a PID controller, the proportional term, the integral term, and the derivative term, in the form of a circuit. Now, let's get into what you should be able to just work right through prior to the final or on the day of the final. If I give you a system in a block diagram, or I give it to you in differential equations, or if I give it to you in a state space, you should be able to go back and forth between any of those representations. You can even go from the transfer function to a block diagram and then to a state space, an all-integrator block diagram, and then a state space representation. If I give you an integrator block diagram, all-integrator block diagram, how do you define or determine a state space representation? This is homework number 10, I believe. You have to do this. How do you create a state space representation from a block diagram, an all-integrator block diagram? What's the first step? You could do a transfer function, but a transfer function is not going to get you, that will get you a model, which is another way of describing the system from a block diagram. But now if you want a state space representation, the transfer function gave you poles and zeros, which is maybe how you want to design the system. But if you don't want a transfer function, if you want the A, the B, and the C, how do you create that from an all-integrator block diagram? Did everybody hear that? I didn't. But I'll assume that my filtering is working. You assign outputs of the integrators to be your state variables. Or you label each output of each integrator as a different state variable, x sub 1, x sub 2, x sub 3. And now, if those outputs of integrators are states, what's the input to those integrators? the derivatives of those states, and there's your x1 prime. You'll just find out what that equals, your x2 prime, etc. We now are given a state space representation for a system A, B, and C, and we could use our cheer to find the transfer function g of s. Or you could be asked, can you find an all-integrator block diagram from that state space representation? Can you draw that? How many integrators would it have? 2. And you might, on your first attempt, get those in weird orders. That's okay. It could have wires going everywhere, but you now need to know that the derivative or the time rate of change of x1 is simply x sub 2. So you could say, oh, x sub 2, maybe I want to be to the left of my integrator representing x1. And then the time rate of change of x sub 2 is minus x sub 2 plus u. And that's not a very complicated block diagram. In our problem that we were talking about last time, we had the design specifications listed as follows. We had 3. We wanted steady state error of 0 due to a unit step. We wanted a settling time of 2%. If I don't say what is your if I just say settling time, assume a 2% settling time, which represents or corresponds to how many time constants? 4, approximately. So now we're dealing with 4 time constants. We want to be 1 second, and we have a percent overshoot of 5%. The highlighted pieces that are written in green show us what you can infer about the steady state error based on your system type. And what defines the system type? How many poles you have at the origin. If you now have a type 0 system, your steady state error is this 1 over 1 plus k sub p, where k sub p is the limit as s goes to 0, and this g of s now incorporates the controller and the system itself. And then you would have, if a type 0 system, it's going to be hard to obtain 0 steady state error. If you have a type 1 system, then you have 0 steady state error due to a constant, and you have a fixed or some bounded steady state error due to a ramp input, where the blue might be the reference input. That's where you're wanting your system to move to, and the red now is your actual, and the difference between those after the transient decays is your steady state error, and that's 1 over the velocity error constant, where your velocity error constant is this limit as s goes to 0 of sg of s. What's the system type for this system? And you could get that from either the transfer function, we have 1 pole at the origin, so it's a type 1 system, or if you looked at the eigenvalues of your A matrix and you remember that a triangular matrix, the eigenvalues are on the diagonal, you can visualize and see, or by inspection, see that you have an eigenvalue at 0 and an eigenvalue at -1. And that corresponds to your poles. And so from the A matrix, you could actually say, oh, this is a type 1 system. Type 1 system now says, oh, if we're using output feedback, we can achieve 0 error due to a constant input. Once we have those 3 design specifications, we can start to translate those into desired closed loop pole values. From the settling time, which was 4 tau, that's 4 over sigma, or now that gives us sigma. And what's sigma? What are you seeing when you hear sigma in this classroom? Hopefully you're maybe gesturing or you're visually seeing this vertical line in the left half plane. That tells you the distance you are into the left half plane. That's the sigma. We're now to the left, our closed loop poles, we want to be at or to the left of a value of -4 in the complex S plane by that sigma. Percent overshoot, what do you see with percent overshoot? Do you see anything? This is now the angle. You may see figure 5.7. You're going to be waking up in the middle of the night and seeing all of these things. Percent overshoot, zeta, theta. That's fine. That's what you want. Or sigma. You might wake up and you may go sigma, sigma. That's okay. That's what you want to be doing. But now you know you're somewhere in the left half plane by a sigma value. The percent overshoot of 5%, if you calculate it, if you don't use figure 5.7, if you now say I want a percent overshoot of 5%, you could put it into this zeta formula. Don't forget the 1/2. Don't forget to take the square root, so I put that in red. Or if somebody gives you a zeta, you could now figure out what the percent overshoot is. And when are these formulas accurate or more reliable? One, the system has to be stable, but what kind of a system are these formulas created from? A pure two-pole system. No zeros, just two poles. These are all just approximations based on a pure two-pole system. So don't think that, oh, my poles are right here. Well, if you have more poles than a zero, it may not follow this percent overshoot behavior that you see from this figure or somewhere else. Now, if you see a 5% overshoot, you may immediately be seeing a theta of 45 degrees. You may be thinking that, oh, a 5% overshoot, that's a zeta of 0.7, that's a theta of 45. If you have 45 degrees for your angle and a real part is -4, you now know the omega sub d value. You now know that you want your desired poles to be located at -4 plus and minus J4. What have we talked about in this class? We've done output feedback or a cascade controller, and what, besides the typo, what kind of a controller is this? Trick question. Trick question. What kind of a controller is this? So now if you have a coin that has phase lead on one side and phase lag on the other, you flip it, you're going to win. Right? Unless you know what the value of Z sub C is and what the value of P sub C is, you just know that this is phase lead or phase lag. If the zero is closer to the origin than the pole in that controller, what controller do you have? Now you have a phase lead. You're trying to draw the root locus further into the left half plane. If your pole is on the origin or closer to the origin than your zero, then you have a phase lag. What's this? The diagram in black is the all-integrator block diagram from the state space representation from before. And the blue is our full state feedback controller with a reference input. And what we want to do in chapter 11, or homework number 10, is determine these k values, k sub 1 and k sub 2. Why are we doing that? Why are we picking K1 and K2, or why would we maybe want to do that? What's the benefit? Where are the open loop poles in this system? Do you remember? 0 and -1. What are you trying to do? Are those acceptable locations for poles? Probably not. You probably want to get that closed loop pole off of the origin if you close the loop. And that's what we're doing with K1 and K sub 2. We're trying to manipulate the system matrix, the A, we're changing it to A minus BK. And we want A minus BK to have eigenvalues where we want them. So let's say, whoops, I was hoping maybe your heads were still down. I think you're still a little bit dazed from this entire semester of material, not in this class, but in general. This class, you're just right on. But if we design a controller for G sub C of S for this system, how do we do that? Where were our poles for G of S? There was our system. So where do we put our X's and O's? Do we have any O's? Or can we label this diagram? You know, if you're just looking for partial credit, maybe that's what you do. You just start labeling. Or if you're trying to wake up. So now we have it labeled. Where do we put our open loop poles? Now I'm getting good at interpreting hand signals. I saw a 0 and, oh, maybe the 1. You want to do that with your index finger. Okay, if you show me -1. All right, so now we have our poles at 0 and -1. Where do we want those to be in the closed loop system? We said we wanted those at -4 plus and minus J4. And if we just had a gain controller, where would our root locus be? If we had no zero factor and no pole factor, if we just had K, what would our root locus look like for this system? These two would come together and just go up, and they would meet halfway between, wouldn't they? That would be our gain-controlled system, and the red line indicates the possible closed-loop poles. That's not going to get us through those triangles, so we have to introduce a 0 and a pole. And now I have to erase one of those arrows. Well, that's not too bad. I didn't erase the whole diagram yet. So now what do I do? What's a quick strategy on the final exam? You only have 2 hours for 15 problems. You probably want to cancel that stable pole at -1. And now what? Now you know that if you put in one more pole, you again have this pure two-pole system behavior, and you know exactly what that root locus looks like. And you would then locate the pole there. This one would march towards the right. This one would march towards the left. They would meet. Oh, boy. That's supposed to be a straight vertical line. If you get far enough away, maybe it looks vertical. But now that's now our root locus. How do we find the gain? So now we've found Z sub C is 1. P sub C is 8. So this is now 8. And if we find the gain K to get us to that triangle, it would be 32. And now we know what our controller is. And that didn't take too long to produce. We now have a controller, output feedback, that puts us at the triangle. And now our closed loop poles are at -4 plus and minus J4. It's a pure two-pole system because we've canceled that pole with a 0. We don't have a 0 really in the system. It's canceled by the pole effectively. And we will have a 5% overshoot and a settling time less than 1 second. What about in the full state feedback case? Now what are we doing? We're trying to find K1 and K2. What's the difference between full state feedback and output feedback? What's the distinguishing property between this picture and that picture? So in full state feedback, you are assuming that you have access to every one of the outputs of your integrators. In the output feedback, you're just assuming you're measuring the output signal. You're not going internal to the system and extracting or pulling off all of the state information. Meaning, you should be able to do more with full state feedback than you can with output feedback. But in many practical scenarios, you do not have access to all the state variables. Maybe you can't have the engine temperature, and that's a part of your model. In this case, we want our closed loop poles to be at -4 plus and minus j4, our desired polynomial we can find as s plus 4 squared plus 4 squared. And now we need to equate that desired polynomial with the characteristic polynomial that we obtain by finding the determinant of Si minus F. And you should be able to do that for a 2x2 system on the final. You should be able to find the determinant of a 2x2 matrix. And you need to in order to now find an equation or an expression that involves K1 and K2, and performing the determinant, now we have S squared plus the linear coefficient of S, 1 plus K sub 2, and we want that to be 8, and the constant coefficient we want to be 32. And we pick the N to give us a DC gain of 1. Where to find the DC gain, what would our transfer function be? Or what is T sub C? Do I have that anywhere? I guess not. So T sub C of S, in this case, is our cheer, but we just modified it a little bit. It's our output matrix times Si minus, and now it's the F matrix, which is A minus BK, inverse times B times N. We might know everything after we found our K values. We know everything in this expression for our transfer function except the N, and that's a scalar. If we want the DC gain of that to equal 1, at what value of S or values of S are we evaluating this? You're doing it at T sub C at S equal to 0. So that now you have this expression that contains one unknown parameter N, and you're solving that so that that one expression that involves N must equal 1 at the value of S equal to 0. What if we wanted to do this in MATLAB, which you might want to do? Is this easier to read with the grid or without the grid? It's fine. You have young eyes, good. Okay, let's have a reading assignment. Now we want to put in our system in transfer function form, that's the TF. The first argument in the transfer function, or the TF function, will be our numerator, and in this system it was 1. And then the last one are the 3 coefficients in our whole polynomial, which was S times S plus 1, or S squared plus S plus 0. So we now have 1, 1, 0 for our denominator polynomial. And we created a transfer function, a phase lead controller, with a gain of 32, a 0 at minus 1. So we have this polynomial expressed as bracket 1 comma 1. That's s plus 1. And our pole factor was s plus 8. That's our controller, G sub c. We want to combine our plant and controller. And that now gives us, so this is now G of s. And this guy was just a 1 in terms of the arguments. Here is G sub c. And L gain is just the product of those two, which is now just giving us the product of those two transfer functions. And we need to put the unity output feedback around that, and MATLAB has this feedback command which will allow that to occur, so that now we have and this, if this is now T sub c of s, which is y of s over r of s, that's what this is. And we can find the poles of our transfer function by just issuing the function pole, and now we have poles at -4, and -1. What happened to that closed loop pole at -1? Scroll down. It was canceled by the 0, wasn't it? So it's not influencing our transient behavior. The closed loop transfer function actually has a 0 at -1, which is canceling that pole at -1. So we now really have two poles effectively, and that's what would produce the desired result, which is in figure 1. And let's see if we can find figure 1 somewhere. There's figure 1. And if you simply right-click anywhere in here after issuing the step command, it will allow you to create or find different characteristics. And one of the characteristics I said is, let me see the peak response. And now I have a peak of 1.04. Does that meet my specification? What was I wanting for percent overshoot? 5%. And what's my final value? 1. So 1.04 is less than 5% for percent overshoot. What was my settling time supposed to be? 1. And who knows what MATLAB uses? They may use a 1% settling time. So our 2% settling time, I would have to go and look. I can't eyeball that. Is that 1% or 2%, those lines around 1? What do you think, class? 1%? Who knows? 2%? But we're close. Our settling time is 1.05. You can also do, this would be now homework number 10. You could work through this in a full state feedback case. Our A matrix, B, C, and D, we can input as matrices. Then we could say, okay, K is equal to 32 and 7, as we calculated. And now we can say F is equal to A minus B times K and get our full state feedback system matrix F. We can compute the eigenvalues of F, which shouldn't surprise us. And now we can say, let's build our system as an object in state space form, and now we have our F matrix, which is the A, the B, the C, and the D. And now let's simulate that. Let's create a time trajectory. And what happens? If we do that, let's look at figure 2. Here's figure 2. Does that look about the same shape as the last figure? Figure 1? Should it look the same? Where were our closed loop poles in this system? -4 plus and minus J for our closed loop poles. And where were they in the output feedback case? Same place. So we should be getting, this is also a pure two-pole system, but what's our final value? What's the output final value in this picture, roughly? Is it 1? No. Quite a ways from 1, isn't it? Which means that if we simply... Oh, I was going to cover up the N. So now if you virtually cover up the N, all we've really done is, or we put in an N equal to 1 in doing that step response. And that's not going to cut it, is it? That's why we need that adjustment in our full state feedback design process in order to obtain maybe what we put in at the output. That's why we need the N, which somewhere in here we have N. Not N for nothing, but N for that matrix. How big is that matrix? How big is the matrix N? It's a 1 by 1 matrix. It's huge, isn't it? It's a scalar, but you could still call it a matrix. But maybe that would be sort of a trick. No, it's not a trick. I'm not tricking you. I'm just saying how big is that matrix. In general, it could be a matrix. Here that matrix is 1 by 1. But now if we sketch that in figure 3, now does that look better? Now we've increased the gain going into that system. We've amplified our reference input of 1. We've scaled it to 32 so that now we know that when we get out to Y, because of our full state feedback changes in our system, we'll now get 1 at the output by using capital N of 32. And this is now the Bode plot of our phase lead compensated system. What's the phase margin of this system? How do we find the phase margin? This could be on the final exam. Hint, hint. So how do you find the phase margin? Or what frequency or frequencies are important if I ask you for the stability margins of this system? What are you looking for? What's going to give you partial credit? Since it's not multiple choice, maybe there will be partial credit, maybe, depending on how generous I feel. But what frequencies are we looking for? Or what parts on these plots? We need to find crossover frequencies, don't we? We need to find the gain crossover, which is right here. Where does the magnitude go through 0 dB? And what's our other crossover frequency? It's where our phase curve crosses minus 180. Where does this phase curve cross minus 180? It doesn't, does it? So what's our gain margin? We have a lot of gain margin. Or we could say it's going to, or is, approaching infinity. We can just keep cranking up the gain and we'll still be stable. What would our system look like if we kept cranking up our gain? Right? It's really going to oscillate. And it will just oscillate faster and faster. We've had a good class this semester. Oh no. So now what do we have? We have infinite gain margin, and if we cranked up the gain a lot, we would just keep increasing omega sub d, right? But we wouldn't change the damping. We wouldn't be going into the right half plane for this two-pole system. What's our phase margin? Change the subject from gain margin to phase margin. Do we have infinite phase margin? What is our phase margin? If we just can you now just say something like that? How big is that? Well, it's bigger than 45, isn't it? Minus 135 is 45 away, and we're about halfway between 135 and 90. So an additional 20 degrees onto that. So are we about 65 degrees phase margin? 61.2? Always, always one in the crowd. Did I do it? Oh, yes, I did. I did the margin command. Margin in Bodhiplot will give it to you, won't it? But on the final, you can't issue a margin command. You can raise your hand and say, may I use the margin command in MATLAB? And I said, yes, you may after the exam. But during the final, you're going to have to come up with this number on your own. But on the final, if you have something between 55 and 70, that's probably okay. Don't get all hung up on, oh, I've got to get exactly the right answer. And that goes for homework number 9. You may not match exactly what the solutions are that they give in the textbook. That's okay. You just need to get some answers. And on the final, you definitely just need to get some answers. Are there questions on what we've covered so far? Are we ready to get into a new topic with the infinite amount of time? We have an infinite time remaining in between now and when we stop. What was I saying that we might cover? Anybody remember? How would we do that? What are we trying to do? Whoa. I can't scroll gently. We have our system. Does that look like our normal system? You should be seeing this mentally. Now, when you envision x dot equal ax plus bu, y is equal to cx, this is what you can maybe see as a block diagram. What's that integral block representing? Many, many, many different integrators. It's a bank of integrators, but now we have x. This is x prime, and so this is x prime is equal to ax plus bu. Y is equal to cx. I've lost everyone. I'm going to crank up the gain now and make you guys shake. But what you would do just if you bear with me you would put an integrator right there, feedback this output, and compare it with a reference. This is now one integrator. And this might be a gain, let's say k sub I. And now you've done your integral control with full state feedback. You would want to find k and use that as part of this feedback, and now you have k sub I there. So this is now integral control with full state feedback. You are free to go, but good luck on your finals, and I'll see you on Tuesday.